We now start the sixth module of chapter 2. In module 5, we learnt about the existence of a basis for a finite dimensional vector space. After that, we proved the very useful replacement lemma, and we saw some important consequences. In this module, we would extend the argument and prove that every vector space has a basis, where we would drop the finite dimensionality assumption. We first proved this theorem, which relates dimension of a subspace and dimension of the parent vector space V. So, let V be a finite dimensional vector space over a field F and W a subspace of V. Then W is also finite dimensional and dimension of W is less than or equal to dimension of V. If dimension of W is equal to dimension of V, then V is equal to W. The proof of this theorem uses the results that we proved as consequences of the replacement lemma in the previous module. So, let us assume that dimension of V is n. If W happens to be the trivial subspace, that is singleton 0, then we are done, then there is nothing to prove. Let us assume that W is non-trivial. Then there exists a non-zero vector V1 in W, and the set singleton V1 is linearly independent. We can continue this process and find a linearly independent subset V1, V2, Vk of W. We know that since dimension of V is n and V1, V2, Vk is a linearly independent subset of W, which is of size k, therefore k can be at most n. Therefore, this process of choosing linearly independent elements from W has to stop after finitely many steps. That is, we must reach a state where we have a linearly independent subset of W, and if we try to increase that set, then we get elements which are linearly dependent on these elements. Then it has to be a generating set for W, because every other element of W would be linearly dependent on that set, and that produces a basis of W. Therefore, dimension of W can be at most dimension of V. If it so happens that dimension of W and dimension of V match, then a basis for W is a linearly independent subset of V with n vectors. Again, by a previous result, we know that if V is an n-dimensional vector space and if we have a linearly independent set of n vectors, then it must be a generating set for V and therefore a basis for V. This shows therefore W must be equal to V. We now see a corollary of this theorem we proved. If W is a subspace of a finite dimensional vector space V over F, then any basis for W can be extended to a basis for V. Proof: we know that every linearly independent subset of V can be extended to a basis of V, and any basis of W is surely linearly independent in V, and therefore it can be extended to a basis for V. We now introduce the concept of maximality with respect to set inclusion in order to talk about existence of bases for vector spaces which are not necessarily finite dimensional. So, definition first, let C be a family of sets. An element A in C is said to be maximal with respect to set inclusion if B belongs to C and A contained in B implies A is equal to B. In other words, A is not contained in any member of C other than A itself. Let us look at some simple examples. Let X be a non-empty set and consider the power set of X, that is the collection of all subsets of X. Then it has only one maximal element and that is X. Another example, let C denote the collection of singletons of a non-empty set X. Then every element of C is a maximal element. And the third example, the collection of all finite subsets of a non-empty set X has no maximal element. Let us now introduce the concept of a chain. So, we say that a collection of sets L is a chain if for every A, B in L, either A is contained in B or B is contained in A. In other words, with respect to set inclusion, every pair of elements are comparable. Let us see this example. Let C denote the power set of the set of natural numbers n and consider L to be the collection of all finite sets 1 to n where n varies over the set of natural numbers. So, we can see that all the singletons like singleton 1, singleton 2 etc. are there in L, and also all the sets having two elements which are of the form 1, 2 and then having three elements, that is 1, 3 and so on, are there in the set L. Then L is a chain for the reason that if we take any two elements from L, typically they would look like set containing the first n integers and set containing the first m integers in the set of natural numbers, and then 1 to n is contained in 1 to m if and only if n is less than or equal to m. Now, we talk about Zorn's lemma, which says that if C is a family of sets and if every chain L of C has an upper bound with respect to set inclusion, then C contains a maximal element. What is an upper bound? That is an element of C which contains each and every element of L. Zorn's lemma ensures that a family of sets with respect to set inclusion can have a maximal element provided every chain has an upper bound. We now look at some specific collection of subsets of a finite dimensional vector space V. In fact, the collection of linearly independent subsets, and we will apply Zorn's lemma to find maximal elements of that collection, and then we will see that such sets, the maximal ones, do form basis for the vector space. This very method of applying Zorn's lemma, which ensures existence of maximal element, is what is called the transfinite induction. And when we do not have the finite dimensionality condition on a vector space, then that is the only way out to prove the existence of a basis. We start with the definition of a maximal linearly independent subset. Suppose that V is a vector space over a field F and S a non-empty subset of V. Let C denote the collection of all linearly independent subsets of V which are contained in S. If C is non-empty, then a maximal element of C with respect to set inclusion is called a maximal linearly independent subset of S. Here some comments are in order. The first one is that V is not assumed to be finite dimensional. V is an arbitrary vector space over a field F, and with the modest assumption that S is non-empty, it is not at all guaranteed that C, which is the collection of all linearly independent subsets of V, is also non-empty. For example, if S is just singleton 0, then there is no linearly independent subset which is contained in S, and therefore C is empty. And then the question arises, even if C is non-empty, is it guaranteed that C would have a maximal element? We will answer these questions. So let us first see that if V is a non-trivial vector space and S is a generating set of V, then it is sure that S cannot be just singleton 0, because then it cannot span a non-zero vector space V. Therefore, S must contain at least one non-zero vector. In that case, the collection C, which is the collection of all linearly independent subsets of V contained in S, is non-empty. We will prove that the collection C indeed has a maximal element with respect to set inclusion. But again, there is absolutely no reason to think that there would exist only one such maximal element. In fact, there could exist more than one. This is a very important theorem. A subset B of a vector space V over a field F is a basis if and only if it is a maximal linearly independent subset of V. So this really characterizes a basis of a vector space in terms of a maximal element. Let us prove this statement. Let B be a basis for a vector space V. We first prove that B is a maximal linearly independent subset of V. B being a basis is definitely a linearly independent set of V and also a spanning set of V. Therefore, B is linearly independent, and if we choose any vector V from the vector space V but which are not in the set B, then B union singleton V is definitely linearly dependent. Why? Because B spans the whole vector space V, therefore that little vector V can be written as a linear combination of finitely many vectors in B. This proves that the set B is a maximal linearly independent subset of V. So where is the maximality coming into the picture? Because even if we increase that set B by one element, then it is no longer linearly independent. Therefore, the set B is linearly independent, and loosely speaking is the biggest possible in terms of set inclusion. Let us prove the converse now. Let B be a maximal linearly independent subset of S, and we prove that B is a basis for the vector space V. Therefore, the set B is a maximal linearly independent subset of V. Why do we call it maximal? Because B is linearly independent, and naively speaking, B is the biggest one possible in the language of set inclusion. Why? Because if we take any single vector small v which is in the vector space V but not in the set B, then we have seen that B union V is no longer linearly independent. Therefore, we cannot increase the set B maintaining its linear independence. Let us prove the converse now. Let B be a maximal linearly independent subset of V. We want to show that the set B is a basis of the vector space V. It is already linearly independent. We only have to show that B is a spanning set of the vector space V. So, it is enough to prove that V is contained in the span of B. So, suppose not, then there would exist a vector V in the vector space V such that V does not belong to the span of B, which means that the vector V cannot be written as a linear combination of finitely many vectors from the set B, and therefore, the set B union singleton V is linearly independent. But then it contradicts the maximality of the set B. Therefore, this cannot happen, and therefore, span of B is equal to V, that is, the set B is indeed a basis of the vector space V. Now, the next theorem says that if S is a linearly independent subset of a vector space V, then there exists a maximal linearly independent subset of V that contains S. So, first of all, if F denotes the collection of all linearly independent subsets containing S, then that collection F is non-empty, because S being linearly independent, S belongs to this collection F. Now, we consider a chain L in F, and our plan is to use Zorn's lemma to prove existence of a maximal element of the collection F. So, we therefore have to prove that the chain L has an upper bound. Let U denote the union of all members of L. So, what is L? L is some collection of linearly independent subsets which contain S. And what is U? U is the union of those subsets which are in L. Therefore, U must contain S, and not only that, U being the union of all members of L, U contains each member of L also. Now, to show that U belongs to the collection F, we have to prove that U is linearly independent subset of the vector space V. How do we do that? Take any finitely many vectors V1, V2, Vn in U and scalars A1, A2, An from the field F, and suppose that the linear combination A1 V1 plus A2 V2 dot dot An Vn is equal to 0. To show that V1, V2, Vn are linearly independent, we have to prove that the scalars A1, A2, An are all 0. Now, U being the union of all members in L, we can say that there exists some AI in L such that Vi belongs to AI, and L being a chain, any two members in L are comparable with respect to set inclusion. Therefore, among the finitely many A1, A2 and so on An elements of L, we can say that there exists an element AK in L such that AK contains AI for all I equal to 1 to n. The vectors Vi belong to AI and AK containing all the AIs, we can say that all the vectors Vi belong to AK. But AK is a member of L, therefore AK has to be linearly independent. This shows that the above linear combination of V1, V2, Vn cannot be anything other than the trivial linear combination. That means all the scalars A1, A2, N must be 0, and therefore U is linearly independent. We have already seen that U contains S, and now we have proved that U is linearly independent. Therefore, U is an element in the collection F, and surely it is an upper bound of the chain L with respect to set inclusion. So, Zorn's lemma is applicable in this case, and it implies that F has a maximal element. It is a very important corollary. The corollary says that every non-trivial vector space has a basis. Well, since V is non-trivial, therefore there is at least one non-zero vector small v in the vector space V. If we take the set S to be singleton V, then S is definitely linearly independent. And by the previous theorem which we have proved just now, there exists a maximal linearly independent subset B which contains S. And we have already seen that maximal linearly independent subset of a vector space V is a basis for V. Therefore, V has a basis. So, we see that we need transfinite induction, in other words application of Zorn's lemma, to prove the existence of a basis for an arbitrary vector space or an infinite dimensional vector space V. We have seen before that if V is finite dimensional, then a finite inductive argument works for proving existence of a basis. But when the finite dimension assumption is missing, then this is indeed the only way out. And now comes the question that if we have a non-zero vector space V, then is it true that any two bases have the same cardinality? In this case, the bases could be infinite sets. So, what do we really mean by saying that they have the same cardinality? It means that there is a bijective map between any two bases for the vector space V. And it is indeed true. We can prove an analogous statement of the replacement theorem to show that any two bases for an infinite dimensional vector space have the same cardinality, or in other words, there exists a bijective map between any two bases for V. Therefore, cardinality of a basis is well defined, and that cardinal number is called the dimension of the vector space. We now conclude chapter 2. We have introduced the notion of linear independence, spanning set, basis for a vector space V. We have proved that every finite dimensional vector space has a basis. We have proved a replacement theorem, which is really useful, which has several important consequences. And finally, we have proved that every vector space, finite or infinite dimensional, has a basis, and that we could do using transfinite induction. Now we move on to maps between two vector spaces. We will start a new chapter and we will talk about linear transformations between vector spaces.